Hey girls, so tomorrow we're going to start a new topic called sequences in a series. Just to get it out of the way, the only difference is what I've actually drawn here is a sequence. It's just a listing of things that have an order. So the first term is 1, the second term is 4, the third term is 9, and the fourth term is 16, and so on, and that's the notation. T with a little subscript n means the nth term. So in this example, the nth term of this sequence, hopefully you can see, is n squared. So if you then asked me, well, what is the 10th term in the sequence, I would say, all right, T10 is 10 squared, which is 100, and so on. If I wanted to turn it into a series, and the general rule would be that the series is normally considered to be a sum, but that notation is not actually important for you guys, so I wouldn't worry about it too much. And that's a pretty standard problem, the one we've got there, but more often than not you're actually given the equation of the series. So for example, you might be told, all right, Tn equals, 2n minus 3. So then T1 would be minus 1. T2 would be 1, and so on. And then I might say, what is the 99th term or something? And so you'd say, all right, T99 equals 195, I think, if my arithmetic's correct. So that's a pretty standard problem. Another standard problem that you will come across is exactly the same thing without a formula, and you're expected to kind of pattern spot. So let's say I said that a series was 4 plus 7 plus 10, and it keeps going on, and I said, what's the 20th term? Okay, so for the first term is 4, the second term is 7, and you can see the pattern, I hope, is that I add 3. So to get to the second term, I've started with 4 and I've added 3 once. To get to the third term, I've started with 4 and I've added 3 twice. So to get to the 20th term, I've started with 4 and I've added 3 19 times. 61, I think. That's another pretty standard problem, and that's actually called an arithmetic series or an arithmetic progression, and that's one half of the major component of this topic. So arithmetic add the same number every time. So examples are 5, 12, 19, 26. And we could work out a formula for the nth term. You start with 5, and then you add 7, n minus 1 times. Another example could be 100, 99, 98, 97, and the nth term would be 100 minus n minus 1. And I'll give you a better idea of how to generate these formulae tomorrow, if you can't quite see it yet. If you can, that's awesome. This thing here, notationally, this is called the first term, because it is always the first term. This here is called the common difference. And the whole point of an arithmetic progression is that every number has the same difference from the number after it. We also later will have geometric progressions. So a geometric progression, which I'll just call GP for now, would be something like 1, 4, 16, 64, 256. And so on, where I'm multiplying by 4 every time. Or you might have like 1, 1/2, 1/4, when I'm multiplying by 1/2 every time. And there's a bunch of other types that I can do. The last thing I want to quickly show you is called the sigma notation. So sigma, you can think of as shorthand for sum. And so it looks like this. So let's say I wanted to sum up values for k, and I want k to start at 1, and I want it to go to 10. So this will be 1 plus 2 plus 3 plus 4 plus 5 plus all the way up to plus 10. And it turns out that will be 41, no, 55, sorry. And I could do a similar sum, so I might want to sum up some squares from k equals 1 to 4. So that would be the sum of 1 squared plus 2 squared plus 3 squared plus 4 squared. Okay. I don't need to start at 1 every time, but you tend to start at either 1 or 0. The only thing that does happen is that every time your input into k only goes up by 1 every time. That's a definitional component of the sigma notation. Okay. So tomorrow we'll just be talking about those things and doing a few examples and probably developing a few formulae depending on how far we get. Okay. So have a nice night, and I will see you tomorrow.